People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencaster. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencaster is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencaster's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencastr.com/pricing and use my code BREAKINGMATH, and you'll get 30% off your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story. Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencaster. Zencaster is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencaster has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word, Breaking Math. Go to zencastr.com/pricing and use my code BREAKINGMATH, and you'll get 30% off of your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your...
Mathematics takes inspiration from all forms with which life interacts. Perhaps that is why, recently, mathematics has taken inspiration from that which itself perceives the world around it, the brain itself. What we're talking about are artificial neural networks. Artificial neural networks have their origins around the time of automated computing, and with advances in hardware, have advanced in turn. So what is a neuron? How do multitudes of them contribute to structured thought? How can they be simulated by computers? And what is then their future? All this and more on this episode of Breaking Math. Episode 14, Artificial Thought. I'm Jonathan.
And I'm Gabriel.
And today we have a new guest, and his name is...
John Gabriel Baca.
Yes, believe it or not, his name is a mashup of the hosts' names. So, Gabriel, what's your deal?
Me?
Yes. I mean, not Gabriel. Jonathan.
Okay,
I've
so
already forgot the guest's name.
Right, so for clarity's sake, I figure I'll go by John, which is what I go by on a daily basis. So we have Jonathan, John, and Gabriel.
Yes, absolutely.
Will that work?
That works just fine, I think.
All right, well, thanks so much for having me. I love the show, and I'm super excited to be on.
We are thrilled to have you. Now, tell us, Sean, you are currently a student at the University of New Mexico. Is that right?
That is right. I'm studying journalism, and I work at the Daily Lobo, the UNM's student-run newspaper.
Excellent. Now, you do have prior experience with podcasting, isn't that right?
Yep, just a little bit. Been dabbling for a couple of years now, but I've not had quite the success that you guys have had, so I'm super pumped to be on such a prestigious podcast.
Oh gosh, we are honored to have you. We are honored to have a student studying journalism, and also I'm really excited because we've had some chance to talk about some, not to go off on a tangent here, but some future involvement with the university and podcasts in general. So we are very, very excited about that. We're certainly glad to have you here, John. So essentially, on today's episode, we wanted to bring John specifically as a non-expert. Jonathan, the host of Breaking Math, knows a lot about neural networks. He's in fact written a few. I know very, very little, aside from the fact that I've spoken to Jonathan about it. And John knows nothing, and that was very much intentional because we wanted to have somebody who could speak for an audience member who might not know a whole lot about it and can tell us, whoa, can you guys slow down there?
Yes.
Now, the thing is, you might say that I know a lot about neural networks because I've written a lot of them, but the truth is, nobody really knows much about neural networks. They just kind of work magically. Like, honestly, let's say it has 100,000 neurons, which is common. That's like having a formula with 100,000 variables. How do you even process that? You have to look at, metadata, things like that to see what's going on. You can't really see what's going on directly.
Yeah. That's fascinating. So even though there's a lot of mathematics that we understand, this is a field where it's used very, very frequently in this day and age. In fact, Jonathan, how many things can you think of that specifically use neural networks? Does Google uses it, right?
Yeah, especially in their self-driving cars. You can't have self-driving cars without RNNs, recurrent neural networks, which means neural networks are connected to themselves. Mm-hmm. The cat versus dog challenge.
I'm not familiar with that.
It's a challenge where you could try to tell the difference between pictures of cats and pictures of dogs. And that uses neural networks. There's pretty much no other way to program that. It's back in the 50s, I can't recall his name right now, but he thought that the problem of identifying objects from pictures would take his students a month.
In this episode, we will be discussing neural networks, what they are, how they work, their history, and some applications for them. To do this, we are going to discuss what a neuron is in nature, as well as what an artificial neuron is in the world of computer science. We will discuss both types of neurons, how they work alone, as well as how they work together, and how they are both similar and different.
Also, why are we doing this on a math episode?
Because using different types of neural networks, any mathematical function or process can be modeled. This will be explored.
And finally, we will go into what place neural networks have in society, which includes security applications, reverse photo recognition, and everything you may have heard about deep learning.
Which here means finding patterns deep in information.
All right, so what we're going to be talking about right now is the history of real neural networks and what they could teach us about artificial ones.
All right, so for the next part here, we're going to jump into the history of neural networks. This is actually pretty exciting. This is less than 100 years old, right?
Okay, so neurons were first discovered in the late 19th century by Santiago Ramón y Cajal, which I guess he was some kind of scientist.
Yeah, he actually did a lot of research. In fact, did you know that he did researched how the eye processes visual information? Basically, he had an experiment that involved spinning glowing coals, and he noticed that even though you've got a single coal, as you spin it at a certain rate, it begins to look like a complete circle, kind of like a sparkler. We all do that with sparklers, right?
I noticed that.
Yeah.
Awesome. I didn't know that about Santiago Ramón. I do know that Gödel, in his theory of color, talks a lot about how dark things look bigger than light things. And that's a lot of the history of neuroscience is that kind of thing, making weird little observations about the way that we see things. I mean, that's in some ways the history of philosophy itself.
Fascinating. So part of this is due to the neural networks of our own brain, but then part of it is the fact that, our brain takes in discrete information. I mean, there's so many reasons why we see things the way we do, and so many reasons why what we see may not necessarily be the way nature is itself.
So let's talk about Horace B. Barlow. Basically, in 1953, he attached a speaker to a frog's eye, technically to a frog's retinal ganglion cell, and he exposed it to different stimulus, and he knows that it had different sounds.
Now, this is fascinating. May I ask? Sorry, just from hearing that story, I'm confused. What was his initial? What was he initially testing?
I'm not sure what his goal was. I think that very often in science, the goal and the discovery are very tenuously related. But
Yeah, what possible hypothesis could he have been testing by doing this, I wonder?
I think he just wanted to know what happened. I mean,
And why use sound on a frog's eye instead of light?
actually, that's an interesting thing. Visual information is as core 5-dimensional on a 4-dimensional manifold. I think I'm getting that right. I'm sure somebody will correct me.
I'm lost on that myself. We can explore that later, obviously, but that's we'll need some unpacking.
Yeah, but basically what it is we have all these. You can think of the back of the eye as a theater, and you have the projection on the back of the eye, which is what you see. And if you extrude that over time, so just imagine a ball moving, a movie of a ball moving in a circle. It's a white ball moving in a black background. Now imagine that extruding and turning into a spiral behind the movie theater. That's exactly what I mean by 3-dimensional visual information. Whereas auditory information is 2-dimensional. You have time and you have volume. In some ways it is a 3-dimensional because you have frequencies, but that's processed, and that's what we're going to be talking about too with the visual cortex.
Okay. So then back to this guy here who was doing experiments on frogs. So he had a frog eye that was hooked up to a speaker, right? And then he didn't intentionally do this, but didn't he get some kind of a feedback when he paced in front of the eye?
I can't remember if he was pacing or if I'm pretty sure he was pacing. That's the story that I heard. It might be apocryphal, but then he heard bzzz or something. I don't know what the sound would actually be.
Okay, now of course that sound would be produced electrically. Obviously that's how a speaker works. So basically, he found out from that information that the frog eye could decipher his movement in passing in front of it.
Yeah, and he noticed that there was a lot of stuff about frog eyes that were specific to the ways that the frogs actually do. And it's important to note here that eyes in different species do different amounts of processing. In humans, we do almost no processing in the eyes.
Okay, and then in a frog, they actually do processing in the eye itself?
Yeah.
So this eye was like somehow disconnected from the brain of the frog? Or how did he know that it was being processed in the eye and not the brain?
Because he connected it to the retinal cell. It was established at this point that neural signals travel through neural bundles.
Now that I think about it, so I think about frog eyes. Now I have full disclosure here. I only can think of Kermit the Frog's eyes, and I know how it has those two
weird little
I've always wondered
pupils.
about that. Yeah,
the reason why is because frogs tend to be prey. If you look at, for example, goats, they have horizontal slits in their eyes.
Yeah, goats have some weird eyes.
Oh, wow.
Whereas crocodiles, which are predators to the max, have vertical slits. Vertical slits are better for identifying very accurately where something is, whereas horizontal slits are very accurately representing if something is.
I have this sad image in my head right now. I'm thinking of Kermit the Frog on an operating table. Oh, I want to get this out of my head. Anyways, there was a lot of important information that we found out from this experiment.
So the point is that he was kind of getting in between the eye and the brain by going straight to the cells at the back of the eye and seeing that they were actually processing information.
Okay, so and then
is that right?
What he found out that we didn't know before was what? Just that eyes have signals.
Well, the eyes have signals that they could process things like stripes, that they could process on versus off, that they could detect objects at certain distances, that they work together. So much was learned, and the paper is called, if you would like to read it, "What the Frog Eye Tells the Frog's Brain."
What the frog eyes tell the frog brain.
So this is interesting. So basically the frog's eye was acting as like a small brain. I mean, that's way simplified, but
I mean, essentially,
it's
yes.
doing some processing
It's
removed from the brain itself.
Well, why don't we talk about the visual cortex?
Okay. By all means.
The visual cortex is divided into layers. And the first one is, it basically detects edges and contrast. That's all it does. So you look at like a box and actually do this right now. Look at something in your in the room that you're in, or
If
you're outside, wherever.
Keep your eye on the road, but
Yeah.
you know, look at the license plate on the car.
Yeah, so you're going to see dark and light pieces, but the contrast, you know, where the edges are, that's detected by the first layer of the visual cortex. Then you have the second layer of the visual cortex, which takes that information and processes it even further. So it does things like find patterns, sees the shapes of things, how they're oriented, things like that. So that's layer 2. And then after layer 2, it gets really fuzzy about what does what. We're still not very sure.
Fascinating. Okay, and then bringing this back to bringing this back to both neurons and neural networks. How did this begin our understanding of neurons?
Well, what this did was it told us a few things. For example, I mean, before his experiments, we knew that the frequency at which a cell fires is directly related to the amount of light going into the cells. So we knew that cells fired. We knew that it had a maximum firing rate, which is related to what's called the refractory period. We know that it's possible for neurons together to. I mean, we knew this. We knew this essentially forever ago, but this is how we started learning how this is done, how they work together to create more thought. Because I can tell you how a neuron works, and we're going to actually go over that. But the question isn't what does a neuron do? It's what do neurons do, and how do they do that?
Very, very important distinction. So again, one more time, you said it's the difference between how one neuron works and how many neurons work together in a neural network, and that's what this episode's about.
So I figure a good thing to talk about now would be, you know, how neurons actually work, like how an individual neuron works.
Yes. Okay. So individual neurons, and this is both biological neurons as well as artificial neurons, and then we're going to talk about how they're different, the two.
Oh yeah, I think we should start with biological neurons.
Sure.
Now, John.
Yes.
What do you know about how biological neurons work? What can you tell me about that?
Well, from what I recall from high school biology or college biology, their cells, they have synapses. Well, they have what are they called? Ganglia, I think, and then synapses.
Those are some fancy terms you're throwing in there. So for our listeners who are not quite so educated,
is ganglia? Is that right? I don't even know.
Ganglia.
It sounded like a fancy cool
ganglia
science
sounds
word.
like a handful of noodles, like all the stringy ganglia, right?
Yeah.
Like is that what it is?
I'm seeing ganglia. I'm not sure if it's what I thought it was, but anyway, they have synapses, and they connect to other synapses from other neurons. The synapse is the space between the little tentacle-y parts of the neurons, and they send electric signals between each other, which is how brains work.
So real quickly then. So when we're talking about a single neuron, essentially it either sends something or it doesn't. Is that right?
Yeah,
Okay.
sure.
Because of the way that they send it, I wouldn't say it's either on or off. I would say because it's on for such a short quanta of time, I'd say that it's when it's on.
Okay.
So it's almost like, your neuron fires, it means to be a very slow neuron, but like at 230, 235, and 237.
So it's not like a light switch. It's more like a pulse.
It's like a light switch operated by a toddler.
Oh, wow. Fascinating. So one other thing. Now, when I was younger, I used to play a game where everybody would get in these big circles. No, I'm sorry. when I was younger, I used to play a game where there'd be two lines of people, and in these two separate lines, everybody would be holding hands. And this was a game where everyone had their eyes closed, and except for the person at the front of the lines. And one of the two was given a green light, and whoever was given a green light, they'd squeeze the hands and they'd send a signal all the way down. And I think part of the game was the tension from, you lose if you sent a false signal. Now, there's some obvious analogies to this game and to neurons themselves, isn't that right?
You're saying that there's an analogy between this game and the way that neurons work?
Yeah. In other words, so one neuron fires and that gives a signal to the next neuron. Kind of like one person can, if you see a green light and you're doing the game correctly, you could squeeze the hand of whoever's next in line. Then they'd squeeze the hand of whoever's next in line, et cetera, et cetera.
A little bit. I think a really good analogy might be to extend that analogy a little bit. Mm-hmm. So let's say that I'm a neuron. And I have a bunch of other neurons, and they're all people in the sense of in this analogy, and they're all connected to me. Now they keep squeezing my hand, and it's annoying me, and it keeps squeezing it more and more and more until I get so annoyed that I squeeze somebody else's hand. That's kind of how neurons work. Oh. They have a threshold.
Okay. So maybe a better analogy could even be like knocking on someone's door until they answer.
Yeah, but then there's actually inhibitory neurons. So there might be, let's say, I don't know, somebody has a crush on somebody, and one of the neurons has a crush on the other neuron. So when they squeeze their hand, it makes them less likely to get mad and squeeze the other hand.
Interesting. Okay, cool. So my analogy wasn't too far off. It was close, but not.
No,
it
was very close. Okay. Especially in the fact that neurons cause other neurons to fire, except when they are sensory neurons and things like heat differences or light causes them to fire.
So basically, we could even break this down into fundamental information. That is to say, so you said earlier, a difference in heat or a difference in light, and that picks up things. Okay, and those are, as you said earlier, that's different types of neurons. Do we know how many types of neurons we have identified?
I am not sure, but I know it's in the dozens.
Dozens?
At least.
Okay, interesting.
So, and neurons are not only located in the brain? Is that right?
Oh yeah, neurons are nerve cells.
Right, so they're through the whole nervous system.
Yeah, whole nervous system. Mm-hmm.
Yeah,
and our eyes, as we discussed earlier.
Yep.
Yeah, I mean, most of them are in the brain, and the brain takes something like 10 or 20% of our calories. That's how much we dedicate to our brain, and that's how expensive these neurons are.
So I have a question. So are neurons basically is it like a binary system where it's either 0 or 1, or can they send more complex information between each other?
I'm almost positive that it's either on or off, but the complexity of the information is when it's sent. So, for example, if a neuron sounds like it's a different signal than.
So then what we just did there is that was a bunch of nerve firing, and it was in a different pattern both times?
Yeah.
Okay.
And in the experiment with the frog eye, the firing of the neuron corresponded to more complex things than just on or off. He said that it is hard to not come to the conclusion that it was about the distance that a frog would try to get a fly.
Okay, interesting. So essentially, and actually, I am right here on this paper. It says we can describe neurons as being both binary in a biological system with a smooth time component and non-binary. And as Jonathan, as you said, in the fact that a signal can be delayed or canceled out.
Yeah, and Alan Turing actually, when he talked about whether or not neurons could be simulated using computers, this is one of the things that troubled him, was the fact that they also the signal itself is there's no such thing in nature as a jump, like something. Okay, there is at a certain level, but normally there's not something just turning on and then turning off.
Okay,
the neuron will go, instead of going, the neuron will kind of go. So it's kind of like if you can imagine like splashing in the water, it goes up and then down and then up again.
Oh, okay.
And then it has a period where it has to rest. It can't, like if you go to this hand squeezing analogy, there's a certain maximum rate that you squeeze hands at.
Interesting.
Because it's all chemical, right? And you need to replenish the chemicals before you can send another signal.
Yeah, and there's like over 100 neurotransmitters that have been identified at this point.
I do realize that we very, very much glazed over neurotransmitters, but then again, the purpose of this episode, of course, is to discuss artificial neural networks. So that's in part why.
Which is interesting because neurotransmitters usually say whether or not something is inhibitory, like dopamine, or excitatory, like norepinephrine. And in artificial neural networks, these are just numbers. So in a certain sense, they are simulated. But we could talk about that in just a moment.
Yeah, and actually, the crux of the episode, of course, is how it is that the artificial neurons are different than real neurons. Not only that, but obviously how artificial neural networks are used in current technologies today.
Do you think, or do we know, it sounds to me, I mean, I'm assuming that natural neural networks are much more complex, can do much more complex things, and can learn a lot faster than any artificial network that we have.
Oh, by orders of magnitude, yeah.
Is it these chemicals and the differences between them that makes them more complex than just like a binary system with numbers?
That's the thing, we're not sure.
That is an amazing question, John. I hope you don't underestimate how awesome that question you asked is, because essentially what you're asking is a chemical or a material component. And ordinarily, I would say that a digital component can always outperform a material component. But of course, here we're asking, can we ever have an entirely artificial simulated neural network that's written in Python or a programming language outperform so is it safe to say that we are not at a stage where we can properly say whether it can or it can't?
Well, one thing we could look at is metrics. How fast, for example, in the human brain, can things turn on and off? We could look at things like seizures to see that kind of information.
Yeah.
In a computer, for example, there's these things in the brain called cortical columns. If I recall correctly, there's about 80,000 of them, and it would take a supercomputer a few hours to simulate what one cortical column does in a few seconds.
Wow.
At least it would a while ago. So just in terms of simulating what neurons do, computers are nowhere close. But there's also the question, what do we actually need to simulate about neurons? Are neurotransmitters actually important to simulate? Or is it, or the weights, which we're going to talk about, fine? For example, when we model a ball that's bouncing, we don't have to care about the color of the ball if we want to know how the time that it takes to fall.
That's a good point.
Yeah. You know, I do want to ask you one thing really quickly. So oftentimes a major theme right now with artificial intelligence and the advent of Watson is, you know, we often talk about when computers and when artificial intelligence will surpass us. And the way you just described it, it sounded like, if I'm not mistaken, it's still a very, very long ways off. But is it still an inevitability?
I believe that it is, and it's not as far off as you might think, especially if computers keep doubling every 18 months like they have for the past 40 years.
Following Moore's laws. As you said, despite the fact that you know, even supercomputers have a really hard time simulating even one, and I'm sorry, what was the name of it again?
Cortical column, I think.
Cortical column. Even though a supercomputer right now is not very efficient at modeling a cortical column, in the future, that very much may not be the case.
Yeah, and we don't have dedicated, well, we have some, and actually some of the original dedicated hardware for simulating neurons goes back to the 50s and 40s. But because of the different configurations that we have with artificial neurons, we don't have many like neuron chips, for example, yet, but we will.
Yeah. I also want to ask you, so with respects to the differences between an artificial neuron and a biological neuron, I understand that an artificial neuron can have a smooth, basically the signal is smooth, but it has a stepwise component. Can you explain that a little bit?
Sure. So basically, when you simulate neural networks, you simulate them in steps. So you have time 0, time 1, which might be like 3/4 of a second, time 2, which might be 1.5 seconds. I'm just making up seconds. So you simulate it in steps if you're doing that kind of neural network. There's also the kind of neural network that doesn't use steps at all, that just assumes instantaneous input and output, which is the kind that identifies differences between cats and dogs, for example, most of the time.
Okay.
But the way that an artificial neuron works is, let's say that you two are artificial neurons and you're giving me money.
Okay, so sorry. So John and I are both artificial neurons, and we are giving you money. I'm sorry. How is this analogy set up?
Yeah, why am I giving you money?
Give me the money, I'll tell you.
Okay.
But,
all right. So for the sake of the argument, John and I are artificial neurons. John, can you do an impression of a neuron? It would help me enjoy this process more.
I am an artificial neuron.
That is very convincing. Okay, I'm sorry.
That really was. But yeah, so you guys are giving me money, but then somebody whispers into your ear a number. It could be positive or negative. So now you're either taking away money or giving me money.
Oh, wait a minute. Okay. Sorry, I was trying to put two and two together. Okay, so
let's say, Gabriel, let's say you were going to give me $2.
Okay.
But then somebody whispers in your ear 3.
Okay.
So now you have to give me $6.
Oh, okay.
And you were going to, and John, you were going to give me $4. But somebody whispers into your ear -1. And then so now I'm going to give you $4.
Ooh, okay. I like this game.
Okay. Got it. So that's what you refer to as the weight, yes?
Yes, that's the weight.
Okay. So weight, now that is a characteristic of an artificial neural network. That's not really biological. So as far as we know.
It's similar to biological neural networks because there can be more or less synapses that
based on neurotransmitters, right?
Yeah, that transmit more or less neurotransmitters.
Like hunger, for instance, could make certain signals go off that don't normally, right?
Well, there's a principle in neural networks called in neural theory called Hebbian theory that says that neurons that fire together wire together. So if, let's say, neuron A and neuron B fire simultaneously, then they're going to get a stronger connection.
I have a feeling that has probably been brought up in a lot of self-help books. Is that right? The whole 21 days for a habit, neurons.
Right, and also in addiction stuff, they talk about, they use the analogy of water flowing will eventually create a canyon, and they use that as an example of if you keep doing certain behaviors and patterns, it creates a sort of canyon in your brain where signals will continue to travel through a certain path through the neurons in your brain.
So for our listeners, the next time you have to give a motivational speech, you can quote what's the principal name? The
Hebbian theory.
Hebbian theory, and say neurons that fire together. Oh, sorry, is it wire together? Fire
together, wire together.
Yeah. Birds of a feather flock together.
Snappy.
Sorry. Yeah. I don't know.
Penny saved is a penny earned.
Do some motivational speech about teamwork or something. I don't know. You guys go figure it out.
So you have all this. So now I have all this money. It's in a pot. So just John took $4 from me.
Yes.
And then you gave me $6. So on average, I earned $2.
Okay.
And I win.
Well, yes, but let's continue with the analogy.
So one question: in your analogy, the people that whispered to us, are they other neurons?
No, these are the weights, and
Okay.
they're something intrinsic to you. You can imagine yourself as someone with this schizoaffective disorder or something.
So somebody's always whispering -4 to me.
And the thing is, the number that you said is based on something that you got, and we'll go into that in a second. So I got $2 on average,
Okay.
and then somebody whispers to me another number like 3. So now I add 2 and 3 together, and I have 5. And now I put this through a sigmoid function.
Wait, are you adding? Because we're multiplying.
Yeah, I add.
Okay.
Because you multiply after, but add before, kind of.
Okay.
Getting complicated.
These
enough.
These
Fair
are
enough.
complicated things.
Yeah. So each pass here has a different function. Okay. Go ahead. Sorry.
So anyway, now I have 5, and now I put that through what's called a sigmoid function. A sigmoid function has a function basically takes a number, spits out another number. A sigmoid function, if you put in negative infinity, it gives you there's 2 different kinds. We'll talk about the first kind. It gives you 0. If you put in 0, it gives you 1/2. And you put in positive infinity, it gives you 1. So it's like an S-shaped curve.
Okay, got it. So if you're looking at so you're looking down at the sigmoid function, and the x goes from negative infinity to positive infinity. You've got a fancy little S going on, like a hill. Okay.
Yeah, it looks like a hill.
I like pictures and I like analogies, so that's good. I like hills.
Yeah. So now I put this at the sigmoid function, and now whoever I'm giving money to, I like let's say that it is 5, and let's say the output is, I mean, realistically, you guys wouldn't have given me like more than $1 unless your multiplier was more than 1. But I neglected to think about that. So now let's say I have like 80 cents. And then my multiplier is 4. I'm giving the next person $3.20, and so on. And that's how artificial neuron networks work.
Okay.
So the weight, what is the analogy, or what is the biological side of that concept?
Biological version of a weight, wouldn't that be neurotransmitters?
Yeah,
maybe?
neurotransmitter. How strongly a neuron connects, how more likely it is to make it fire, and whether or not it's going to make it more or less likely to fire.
So like pleasure, like a release of the pleasure creating chemicals after you win something or something like that, that helps to create those habits, I think.
Yeah, exactly.
Okay.
For you, the listeners of Breaking Math Podcast, Audible is offering a free audiobook download with a free 30-day trial to give you the opportunity to check out their service. Gabriel, you got any recommendations?
Absolutely. Today, I'd like to recommend the New Scientist Instant Expert book, How Your Brain Works. This book is put together by Editor-in-Chief Allison George, who is an instant expert editor for the New Scientist magazine. Also, the editor, Carolyn Williams, who is a UK-based science journalist and editor, who is also the author of Override. This book is a book that covers many topics about how the brain works, including memory, intelligence, emotion, sensation and perception, consciousness itself, also ages and sexes of the brain, and sleep, and many, many more. It is a phenomenal and fascinating read.
And if you want to know what happens when your neurons don't work as well as they maybe should, check out Driven to Distraction, Recognizing and Coping with Attention Deficit Disorder. This book helped me deal with my attention deficit disorder, and maybe it can help you too. And either way, it's a fascinating read. The chapters are organized in such a way that it doesn't matter what order that you read them in, so that, you know, if you have ADD, you could still get through the book no matter how bad it is. And to download your free audiobook today, go to audibletrial.com/breakingmath. Again, that's audibletrial.com/breakingmath for your free audiobook. Now, back to the show.
Very good. So then for this next segment, I believe we are talking about just general principles of neural networks in general, right?
Yeah. Given the description that we told you about neural networks, you might wonder, okay, well, what can you actually do with a neural network? Like, what kind of function could you simulate with a neural network?
Okay, to our listeners, we're going to sell you. You are going to be so impressed by neural networks that you're going to be wondering, you're going to be breaking out your credit cards saying, where can I buy one? Right? That's our goal, right?
Yes, you can buy neural networks from, I don't know.
You guys sell neural networks? What's going on here?
I know. No. You're going to be so impressed with neural networks that this is going to be the topic you'll bring up at your next date. Watch us, okay? Just watch. They're really, okay, so without me selling it up, I will let you take the floor, Jonathan.
Well, the way that we wire these neural networks together is you can think of them as in layers. Mm-hmm. So you have your first layer, and that's like, I don't know, like let's say that's like 100 pins on one of those boards that they have during, you know, the police shows when they have the pins on the board.
Oh, yeah, evidence boards. Yeah, all the pictures. You got your hypothesis and your theory, right?
Yeah, so imagine 100 pins.
Okay.
Now, a fully connected layer means that let's say you have a second row of pins, and every pin in the first row is connected to every pin in the second. And then you have a third row. If you have two hidden layers, actually, no, if you have one hidden layer, then you have 3 rows. Yeah. Because then you have an output layer and middle layer and a first layer, and so on. So that's what a hidden layer means. So a hidden layer means that you have 3 layers. Given just 3 layers and enough neurons, the more neurons, the better. You could approximate any function that exists.
Say that one more time, because I think that what you just said is the crux of this whole segment, right?
Yeah, any function using a neural network that just connects forward, just that connects forward, which is not even to talk about neural networks that connect to themselves, can simulate any function possible.
Wow.
So
And get it right exactly?
it could approximate it to any level of
Arbitrariness, right?
yeah. So the more we add, the better it'll approximate it.
Any function at all. You can do that with just 3 layers. 3 layers right there. Top layer, middle layer, bottom layer.
Yeah, and not only that is if the neurons connect back to themselves again, you could simulate any program that you could possibly write with neurons.
Okay, interesting. So should we talk mathy here real quick? Should we? There's a nice sentence here I'm looking at that has a lot of mathy terms.
Sure, let's talk about some math.
Okay.
Given a function f, a tolerance d, a neural net defined using a sigmoid function s, where a is a matrix of weights and b is a vector of biases. Basically, that means that a times the input plus b is the output. And if you have 2 of these layers, so you have a1 and a2, b1 and b2, f of x minus n of x, where n of x is the output of the neural network, the absolute value of that is less than d, and only one hidden layer.
Woo-wee.
And Gabriel, was that really necessary?
You know what I want to add to that? I want to add what's the sound? That woo-wee. Yes, that is some serious math right there. You know, I almost feel like if our listeners are listening in their car, they probably pulled over just to write all that down, right?
Yeah, but here's the cool thing: you don't even need a sigmoid function. Some neural networks use what's called a ReLU function, which means that if it's less than 0, then 0. If it's greater than 0, it stays the same.
That's kind of like the math version of kind of eyeballing it, right?
Kind of, but it works for identifying things.
Yeah, you know, hey, I find in life eyeballing it kind of works more than you think it would. You kind of eyeball it, you know? Okay. So, now, what about things like, you know, with all this transmission of signals, you know, I'm sure a lot of elements of signal processing go into this, including the Fourier analysis.
Oh yeah, using Fourier analysis, you can actually prove the fact that any one hidden layer neural network can simulate any function, and the proof is actually a little bit too difficult for us to go into right now. But if you're mathematically inclined, I highly suggest that you look it up.
Mm-hmm. Nice. Now, and again, I know with Fourier analysis, we often talk about, especially with signal processing, and I don't mind bringing it up because this is a really, really cool topic. So there's the Fourier transform, which will take something that's like in the time domain or something that happens over time, and then it represents it happening in a frequency domain.
So what that means is that it's like changing what you hear into the notes of the music, kind of.
Interesting. Yeah. Okay. And then also with respect to Fourier analysis, I believe that also includes just the Fourier series too, right?
Yeah, and it is used a lot in serious neurology, as is the Dirac delta function, which is something. Yeah. Which is a function that's 0 everywhere except infinity at 0 and has an area of 1.
Yeah, it's like the rules to some weird game that you're making up. But that's part of what math is, right? You know, basically making up the rules as you go, kind of, to explain things.
And in neurology, this is extremely typified. I mean, we've had completely different, versions of how neurons work, different models. They're called perceptrons. So there's so many different ways.
That's a fun buzzword, perceptron. And then actually, this is the first time I've heard it is during the research for this episode. So how do you explain to our audience what a perceptron is?
Sounds like a Marvel movie.
That's right. Well, they've got vision and perceptron. Okay.
But perceptron is just a fake neuron.
Okay. Yeah. As used in a neural network, of course.
Yeah.
Okay, nice. So then why it's cool? Let's talk about why it's cool, shall we?
So let's talk about how these things are actually trained. Mm-hmm. So you have a good neural network. What good is it if it has random weights?
If it's random weights, you're gonna have a mess. I think if they're randomly assigned, I think that you want. Am I speaking the truth?
There's actually a story about randomly wired neural networks. Mm-hmm. And it's from the Jargon File, which we talked about on, which episode was that, Gabriel?
Oh, Jargon File. That was a recent one. I believe we brought that up a few times. The Culture of Hacking, episode 11.
Yeah, and it goes like this.
In the days when Sussman was a novice, Minsky once came to him and as he sat hacking at the PDP-6. "What are you doing?" asked Minsky. "I am training a randomly wired neural net to play tic-tac-toe," Sussman replied. "Why is the net wired randomly?" asked Minsky. "I do not want it to have any preconceptions of how to play," Sussman said. Minsky then shut his eyes. "Why do you close your eyes?" Sussman asked his teacher. "So that the room will be empty." Oh, burn. At that moment, Sussman was enlightened.
So yeah, obviously that's a story about like a neural network, even if it has random weights, is doing something. It might be doing the wrong thing, but it's doing something.
Well, dude, it's about not having, prejudgments from society. I'm sorry.
That was like a mathematical Buddha right there.
Or a mathematical hipster, okay.
It was like a sound of one hand clapping.
Wow.
Actually, there are things called AI cones, which are part of the jargon file.
Artificial. Wow. So I love the jargon file. It's deep, man. It's deep.
But yeah, so the question is, how do we train these neural networks to like? So the thing is, there's three types of learning in machine learning.
Mm-hmm.
There's supervised, where we know the question and the answers, and we teach it a bunch of questions and answers. There's unsupervised, where we just have a bunch of examples and we ask it to please try to find a solution. And then there's halfway between, where you can figure out what that means for yourself. It's halfway between knowing and not knowing. It's where you have some elements that are unknown.
Interesting.
But we're going to talk about the case where you know the question and answers. So let's say we're trying to teach a neural network how to differentiate between cats and dogs.
Mm-hmm.
I showed a picture of a cat. It does its thing, and it says dog, and then we say, nope, it's a cat. Now what happens?
Oh, now let me ask you real quick, just to specify. When you say do its thing, you have a picture of a dog and a cat, and the neural network has some awareness of this. What information does the picture have? Like, has the picture taken in the image and qualified it somehow? You know what I mean? Like by shape or things like that?
Oh, well, the layers of the neurons actually do that. Like, with just one layer, you could identify something like edges. Then with two layers, you could identify, if you're doing video, I don't know, things like acceleration and so on. Each layer adds a ton of complexity in practice, not
very
in theory.
good. Okay, yeah, that's what I was trying to get. So again, when you give an artificial neural network the picture of the cat and the dog, it has an imprint of all the information, and it's categorizing the information as you say yes and as you say no. Yes.
Yeah, and actually, we're gonna play for you real quick a version of Eine kleine Nachtmusik that was run through a visual neural network after being transposed from sound into picture.
So what is that exactly?
That's from Google's Deep Dream, and that's kind of more or less how a neural network perceives what's going into it.
So that's what the neural network is hearing when it's looking at that piece of music. Is that what you're
basically,
saying?
yeah, that's what it might as well be hearing.
Wow. Okay. Trippy.
It is very trippy. But so let's say we have this picture of the cat, and then we say, oh, you're wrong, it's a dog. What we do is we go back. And so like we had the people connected together, everybody knows exactly how wrong they were. And everybody changes how this is a gross oversimplification, but everybody changes their weights based on how wrong they were.
Okay, and you say based on how wrong. So how wrong is only established after several rounds, right? Because, in one round, you just know that round you were wrong.
Well, actually, each round you know exactly how wrong you were because you, for example, in the cat versus dog thing, you might use what's called a binary logistic regression function, which means that you basically say, nope, you're exactly because it gives you a probability that it's like 60% positive that it's a cat.
Mm-hmm.
So that means that if it's not a cat, then it's 40% wrong. And then you take the derivative of that, if you're mathematically inclined, and go back using the chain rule.
Interesting. Okay.
And then you change the weights. That's how and this is discovered in 1975. Before that, you had to kind of evolve random neural networks.
So this is how a network learns or gets better and better at doing its job. The more examples it sees, the more times it gets it wrong, the more it tweaks what it's doing to get a better answer, to get closer to the correct answer.
Exactly, yeah. And for example, in my handwriting program, I used the MNIST data set, which had 60,000 digits. So you need a lot of examples.
And I can just see how telling the difference between a cat and a dog, it already sounds really complicated, but that's actually a pretty simple thing. Like, and then you could take it to, I'm going to show you a picture of an animal, and you tell me whether it's a cat or not, which would become, it seems to me, much more complicated.
Yes, but what's weird about that is that if you have a network that's already trained to recognize the difference between cats and dogs, you can actually take that network and use it to generate to just tweak it a little bit to let it tell the difference between cats and ants,
right,
or something like that.
If it gets really good at telling what a cat looks like, then you could broaden it out and it will still be good at being able to tell what a cat looks like.
Somewhat. There's a lot of research in this area.
Complicated stuff. So how hard would it be to be able to...
Repeat that?
How hard would it be to be able to have a program that you just show it a picture of an animal and you ask it to tell you what kind of animal that is? Is that even like a reasonable thing to ask at this point?
At this point, you would need because that's one of the bottlenecks right now is that we don't have enough identified data. Because basically you have all this data generated basically by grad students that spend a bunch of, or actually sometimes people are clever and use things like YouTube comments to try to identify moments in video and things like that. But that's the thing with even is that if somebody's holding your hand, it's a lot more powerful and you learn faster, but you have to have somebody holding your hand.
Right. So is that what those CAPTCHA, those Google CAPTCHA things are when they ask you, click on the sign, click on the storefront, you know what I mean, before they let you get to the website? Are they gathering examples of what's in a random image?
Actually, that's what they do half the time. Half the time they are actually genuinely asking. Half the time they already know.
Right. Okay.
Which is very clever on the part of Google, especially when they do, like, you could actually mess with Google if you wanted to. I wouldn't suggest doing it because I don't like delaying the progress of humanity.
Right.
But if you asks you for two random words, like a lot of the time you could just type in the first word that it asks and then a random word for the second one, and it'll let you in anyway.
So I think that's just really a great idea. So they basically took something that's kind of a pointless thing, which is just like a security thing, but they actually made it do something useful for society by helping to grow computer learning.
Yeah, and neural networks can do really complicated things now. Like, for example, in a picture of breakfast, they could identify slices of banana. They could identify where the table is, where the forks are, draw boxes around all of it, and then describe the image as a scene of breakfast.
Wow.
Like, they could do all of that already.
And that's what what we would expect for like a walking robot, helper around the house would have to be doing that constantly everywhere it was looking.
Yeah, and actually there's an area of research right now where they tidy up rooms and robots watch them and then try to copy what they do.
Huh. Oh. So to start out with artificial intelligence, we basically have to teach them everything, and like you said, hold their hands. But eventually, it seems like it would get to the point where, like a little child, they would be able to, start taking what we had taught them, and then go from there.
Yeah, which is why I don't think that the first artificially intelligent machine it probably won't be that big of a surprise, because we probably will spend 20 years teaching it, just like a human, how to be a human.
That's fascinating. Unless it already exists. Unless it's already, what MySpace evolved into. I'm just kidding.
Hiding out on the internet somewhere.
No, that's what I mean, because I always talk about the internet, and especially the deep web and all the unaccounted for junk that's still floating around there is basically an ideal digital primordial ooze. You know what I mean? Yeah. Great sci-fi novel right there. Great sci-fi novel. You heard it here first.
I like it.
Yeah.
I like it.
So I think in with respect to these topics, we could go into any one of these topics very, very deeply. However, I was curious about a few more things that are unique to, say, artificial neural networks that you may not see in biological neural networks. Things like back propagation and convolution. Can we talk about those for a little bit?
Sure. Convolution is used in what's called convolutional neural networks.
Mm-hmm.
That's basically where the weights are shared. And they're shared kind of in a grid.
Okay. So when you say shared, the thing I hear obviously is you start with two, at least two, or rather multiple neural networks, right?
You have a layer,
Mm-hmm.
but a lot of the layers, like when that person's whispering the number into everybody's ear, it's one person whispering it into like every fifth ear,
Okay.
or something like that. That's more or less what the convolutional neural network is. And that's actually based on the visual cortex, especially the first layer of it.
Interesting. So then help me to understand with respect to information, how is a convolution neural network different or better or actually rather just different than traditional neural networks?
You mean biological ones?
What can they do that the traditional ones cannot do?
Well, because they both can simulate any function,
Mm-hmm.
and they're both Turing complete,
Yes.
technically neural networks can do anything neurons can. So it's not...
Oh, right. I'm specifically in this case referring to a convolutional. Like I'm trying to basically say, functionally speaking, when would you want to use a convolutional neural network?
Oh, that's when you have, like, for example, if I want to detect edges, I don't care where the edges are.
Okay.
So that's like, I wouldn't want a different type of weight in the corner versus the center. That's when I would use a convolutional neural network.
Mm-hmm.
I would use a fully connected neural network when I want to get very specific kind of intrinsic data about where things are, what things are, how they are, etc.
Wow. Okay. Interesting.
So I'm seeing something here about convolutional networks. They're feed-forward networks. What does that mean?
What that means is, going back to the police board, that they go forward. They don't feed back into.
They don't
themselves.
loop back around and
Yeah.
start over. Okay, I got you.
That's basically. Although you can make them loop back around by adding a loopy component to them, but that's hard to do.
Very interesting.
And all these are trained in essentially the same way. There are, of course, so many variations. There's things called LSTM units, long short-term memory, which are related to recurrent neural networks. I mean, this is a field that has become extremely rich in the last 10 years.
We were just talking about convolutional neural networks. What about recurrent neural networks?
Now, what a recurrent neural network is basically...
Can I guess?
Sure.
It recurs? Sorry. Okay.
It connects back to itself.
Oh. Okay.
So it's something that uses its own output as its input.
Okay.
Which is similar to the to the prefrontal cortex, because most of the connections in the prefrontal cortex are to other cells in the prefrontal cortex, and like there's so many loops in that part of the brain.
Interesting.
What good is doing? What good is that?
What good is that it can simulate any program. So for example, like if I tell you to count every odd number, that's a program, and you could do that using your prefrontal cortex. I could tell you to tell me every odd number that doesn't start with a T. And that's another thing in the prefrontal cortex. It's just a program.
Sorry, every odd number that does not begin with a T.
Yeah.
Okay. Oh, got it. Got it.
3.
Yeah. 7, 9. Yeah. Okay. I get it. So now I'm doing it. So our brain does it pretty quickly. Interesting. So a recurrent one that feeds into itself, kind of like that Irish snake thing. It's like eating its own tail. Something
Oh yeah,
like that.
or Ouroboros.
Or I think of putting your foot in your mouth. I don't know. Okay. Now, I imagine these recurrent neural networks can do some pretty amazing feats. Like they can simulate handwriting.
Yeah, like if you give it enough examples of different handwriting, you could give it an example of your own handwriting and just give it text, and it'll write something that looks just like you wrote it.
Wow, that's amazing. So that for like forgery. Then other examples. And full disclosure, I'm just reading off of a fancy list that may have been prepared by a guy whose name rhymes with Bonathan. This list says it can do amazing things, including data compression or arbitrary image recognition. Now we talked about that earlier. Also short-term memory mechanisms and create far-reaching temporal conclusions.
Yeah. So for example, like let's say I have like something within a parenthetical. And of course, the thing within the parenthetical, if you saw it, if you didn't know about it, would be cool. But if you didn't, okay.
So we're talking about a hypothetical parenthetical.
Nice.
Yeah, and as you can tell by my extremely convoluted sentence back there, I was trying to do a very convoluted parenthetical. And as you can see, it gets very complicated very quickly.
Yep, absolutely. It may take a neural network to understand what we're talking about here.
But that's what they can do. If anybody, there's a structure called XML where basically parentheses have names, and a recurrent neural network, without being told how to do it, can learn XML.
Wow, that's actually quite amazing. Quite amazing, in fact.
It's kind of scary, honestly.
Yeah. Now, isn't it true that like actually every single biological neural network is in fact recurrent?
Every one that we know of, except for little things like when we're talking about the prefrontal cortex and like just little segments of it.
Now that's fascinating. Now I'm sorry, I totally cut you off there. I was bringing up like even insect brains. Those are also have an element of being recurrent in them as well.
Yeah, and because insects need so much automation, their neurons are much more complicated than ours.
It's insane. That's crazy.
So their neurons do more thinking by themselves. In other words,
pretty much. So we're more general. I mean, we're born with almost no information.
So really, what we're all wondering.
So it's
here,
like I'm sorry to interrupt. It's like instinct over learning, having to learn everything. Through experience.
Basically, and humans have to learn. We don't have much instinct.
So how long will it be? Until we have a neural network that is asking, why are we even here? Why do we exist? What's the meaning of all this?
Well, it depends. Did you teach it to say that, or did it decide to say that on its own? And how can you tell the difference?
Well, we decided to say that on our own. At least I'd like to think so. Let's just say the latter. Let's just say it's on its own.
Or it suddenly turns around and says, "Why am I doing this?" Like you tell it to do something, and it says, "I don't want to do this.
I didn't ask to be made." Okay.
What's the point of this thing that you want me to do?
It's really hard to say because we know so little. I mean, we just have started to figure out that if you give neural networks attention, like humans have attention, that they can have useful memories. Like that's something that we just figured out in the last 2 or 3 years.
Okay. So basically, we are not yet at a point where it'll start asking self-reflective existential questions.
No, but the amount of progress that is being made every single year with the neural networks is astounding. In the last 10 years, we've gone to basically knowing that neural networks can do some simple tasks, to having neural networks that can do things that only humans could do previously. That essentially is the history of artificial intelligence, but it's a history that is starting to rapidly catch up with the reality of what it means to be human. And these existential questions are going to be something that we're going to have to wrestle with. And a lot of the functions that neural networks are being used for, and we're going to be trying to be using for, can range from anything from data compression to image recognition to sentiment analysis, where you look at a sentence and you say how sad it is or how happy it is, something like that.
See, as a writer, that really disturbs me because I started getting into writing because I figured in 10 years, this is the one job that robots will not be able to do. And you're telling me that they're teaching robots how to learn to be good writers.
Have you ever read the short story by Roald Dahl?
Which one?
The one where he gets put out of a job by a computer?
No, I have not read that.
Oh,
But
should.
it's a great fear of mine. I know that they already have programs that can write simple sports recaps and also financial stories of just, the stocks did this today. They have computer programs that can just spit those out.
But see, then we have the thing is that if we can interface with these machines, because we are learning how to interface almost as quickly as we're learning how to develop them. So can we use them? Like you as a writer, could you have a neural network that you could work along with you to give you story ideas, to get you out of creative slumps? What's the difference between that and using this bizarre technology that allows you to replicate speech using squiggles on paper?
No, you're right. And, just having Google, to be able to just look up any fact at any moment, people from 50 years ago would look at that and say, oh, you have half of your brain is a computer already,
And I do
see your
remember
point.
things by Google queries sometimes. Sometimes I don't know a fact, but I know how to get to the fact.
Right.
So part of my brain is Google already. So
Yeah. But, my concern is so if you have a computer who's like a writing assistant or something, at what point does it get to the point where you have to put on the cover of the book, your name and the name of your artificial neural network that helped you write the book?
I think at the point where it feels right, I think humans have a sense of justice that's very accurate.
Well, it's going to be pretty complicated to figure out where those lines are, but it will definitely be interesting.
I'm Jonathan,
And I'm Gabriel.
and today on the show we had on
Jonathan Baca, also known as John.
And also Jonathan Gabriel Baca, which is just trippy.
That's true. That's my middle name.
and we're gonna talk to you a little bit about a new part of something that we're a part of.
Mm-hmm. Vaguely.
Vaguely, because it's blank for non-blank.
That's exactly right. Yeah. So blank for non-blank. Now you can fill in the blank.
Yeah, and what's that website?
Actually, it's www.blankfornonblank.com, and it is a podcast collective that we are thrilled to be a member of. The idea behind Blank for Non-Blank is it brings subject matter experts in to talk about subject matters for non-experts. And there is a chemistry podcast. There are a couple of linguistics podcasts. There's your favorite math podcast, Breaking Math Podcast. And there's even a few others that are as of yet to be named, but will be part of it as well. There's cultural and history podcasts. So next time you're at a computer, be sure to check out www.blankfornonblankpodcast. Oh, actually, let me check if it's blankfornonblank.com or blankfornonblank podcast.
Just .com.
Okay. Blankfornonblank.com.
And we're still, of course, part of Santa Fe Trail Media. And we're going to be bringing you the same content as we always have. We alluded to this change last week, and now it has come to fruition.
Oh, and Jonathan Gabriel Baca, did you want to plug anything?
If you live in New Mexico or if you're a student at UNM, just keep your eyes out for a bunch of new podcasts that we have in the works. Gabriel and Jonathan might be helping us with some of those, and we're really excited about it. So just watch that space.
Yeah, and those should be found at the UNM Daily Lobo
at dailylobo.com.
Very
That's
good.
right.
Ow, 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 ow.
Do you freestyle?